Good. Okay, so we're very happy to have another talk today after yesterday's talk by Josh. Today we'll have a second talk on an introduction to special relativity by Abdrock. So whenever you're ready, take it away.
Thank you very much, Chris. Hello, I'm Dominik Śliwiński, and I am very proud to be a part of Gregorius Summer 2022. I've prepared this introduction to special relativity. It is meant to be rather intuitive and also more for your average mathematician, so no much physics knowledge, no physics background, not much of that is required. And it won't be super rigorous. So it's just to give you the general idea of the main concepts in special relativity. So I guess I'll start now. So first we have to talk about the concept of relativity of motion. So imagine me with a feminine body standing on a bus stop. And there's Chris, who is driving a bus with the number 2015 on it.
Why that particular number, if I may ask?
I was wondering this too.
Because it was in the stock photo.
Oh, good answer.
Good ad. Yeah. I mean, so now, for me, as I observe the bus, let's say that this bus goes at a speed of 30 kilometers per hour, or if you're in America, you might use like square-rooted feet per Hamiltonian millions or something like that. But whatever the fuck you're using, let's say it's 30 kilometers per hour. Okay. Now, for me, what it looks like is that the bus is moving for 30 kilometers per hour. But if you think about Chris, as he's driving the bus, for him the bus itself is stationary because he moves with the bus. So his environment that he's placed in, it's moving with him, so it's pretty much stationary. But when he looks at me, I am the one who is traveling 30 kilometers per hour. And that's the concept of motion being something relative. Now, think about my feminine body disappearing, and only my head is left. Now, what would happen due to general relativity, to gravity, which I'm not going to be talking about in this presentation? My head will fall down, and in fact, I have drawn this little arrow, which kind of shows how I will fall down. But notice that this is kind of a perspective of if you had somebody at the other side of the street, right? That's how they would see me going down. But to Chris, who let's say that Chris is moving right? You know, ignore the previous picture when he was going, towards me. Ignore that. Let's say he's going to the right from this picture, right? Now, what would happen is for a stationary person, for me, what would happen is this is how it would look like, right, for a stationary environment. But when Chris is going right, what is happening is that I am falling down, but relative to him, I'm also going to the left. We said that the bus goes 30 kilometers per hour, so that's the speed I would be going to the left at. So that's how my fall will look like for Chris, and this is how it will look for me. Now, take a look. Now, for example, if we kind of switch perspectives, imagine that there is Greg, who is being tossed. Right? So imagine that Greg walks up to Chris and he's like, dude, I've always dreamed about being a bus driver. But Chris is like, no, fuck you. So what he does is he kind of starts holding him and then he tosses him directly to the ground. Now for him, how he would see Greg falling down, he would see Greg going directly down, okay? Because the bus, it's stationary relative to him. However, how I would see it from the bus stop is I observe the bus, and let's say, right, that it's going, I don't know, let's pick an arbitrary direction to the right, right? So, if the bus is going to the right, and I know it will change its direction many times during this presentation because I will never remember which direction it's going. But let's say it's going right, relative to me, and Greg is tossed directly down. For me, how it would look like is he's going down, but also right, because he's moving with the bus.
When you say me, just to clarify in this example, when you say to you it looks like Greg is going down, you're not referring to the version of you that is falling, the headless version of you that's falling. You're referring to now a version of you that's stationary and standing outside of the bus and seeing Greg fall, right?
Yes.
Okay.
Yes, that's what I'm saying. The one with the feminine body, you can imagine like that, right? But okay. Now, we have to mention the main postulate of special relativity. In fact, there's another postulate. This is often titled the second postulate. In fact, there's another one. There's the first postulate, but I will touch on it a bit later in a context that I think it will fit better to clarify some confusion. So, for now, let's discuss this main postulate, which is Einstein's postulate of speed of light. The speed of light is always constant and independent of any observer. It is denoted c and approximately equal to 300,000 kilometers per second. So now let's look at some consequences of this. Now, so imagine that there's me standing in my feminine body on the one side of the street where there's a bus stop, and I look at the other side where there's my head, which has already fallen. And let's say that this head has a flashlight, and it gets the flashlight exactly down to the floor, such that when it lights it, it kind of bounces off, and let's say this is a fucking like invisible flashlight, thinking the light will go through it. What happens is the beam goes directly from the bottom of this bus stop to the top, right over here. Let us denote the height of this bus stop with the letter h. So now, think about the time that it will take for this light beam to go from bottom to the top. Okay, from the bottom to the top. Now we know that we'll denote this using t naught. Okay, and we know that time is equal to distance over speed. Now, what is our distance? Now, it's the distance traveled by this light beam is obviously the height of the bus stop. The speed, however, as mentioned previously, is the speed of light, c. So this is light beam's travel time in a stationary environment. But now, imagine that Chris, or Ferko, is going left, okay? Let's say that the reason why he's changing direction so much is because he's trolling the people that, are at the bus, He wants to be a little funny, do a little trolling. So, what happens as he goes left is how he sees the light travel is it goes up, but it also, since he's moving to the left, right, I would be moving to the right, the light is moving to the right, so it actually goes right. Now, for this to have such a shape, he would need to have a very big speed, because remember, we're talking about light here, but this is just for demonstration purposes. This, graphical representation is pretty wrong in the first place. So, you will actually notice that this makes a right triangle over here, right? So here's the height of our bus stop. Now, this distance, right? What is this distance? We'll recall the fact that distance is nothing but the speed times the time that is, that you take to beat this distance with that speed. Now, we'll let t1 denote this relative time, right, for this light beam to travel from the bottom to the top. And we'll let v denote whatever is the speed of the bus which is driven by Chris, okay? So this is why this is VT1. This is h because of this. Now, what about our hypotenuse? Now, our hypotenuse... Well,
can I interrupt for just 1 sec? Is it possible to like zoom out a little bit or change? Because I can't see the bottom of the diagram where the V is labeled the way the screen share is right now. I don't know if you can either zoom out or scroll down a little bit just to see the whole diagram. It might help a little bit with the argument.
You can't see
You
it.
can
Wait a
kind of
second.
see it in the preview. On the
Yeah, you can see it in the preview, but it doesn't show up in the main.
Yeah.
Oh well, I can do this. Wait a second.
Oh yeah, you can
here.
probably just that's good. Okay, yeah, it'll be
Right.
easier for people watching the recording if they can see the labeled bottom part. Okay, thank you. Sorry about that.
Right. So yeah, no problem. Right. So as I said, this is the speed, right, that it takes for this, and then t1. And now think about this distance, right? So what is our speed? Well, light is traveling here, so it's the speed of light, denoted by the letter c. And the time that it takes it is by definition t1. Okay. So can you still see it?
Now it went away, so I can't see the bottom again. But if you nudge it down just slightly, it'll probably be visible.
But this part is irrelevant for now.
Ah, okay.
So okay. So we notice, since this is a right triangle, we can use the Pythagorean Theorem. We notice that, and thus we can get an equation satisfied by the light beam's travel time in a relative environment. So what we get is VT1 squared plus h squared is equal to CT1 squared. And I could zoom out. Right. These two sides of the squares has to be equal to the square of the length of the hypotenuse. Okay. Now, we take this equation right over here. Now, the first thing I do is I distribute the exponents. So what we have is v squared t1 squared plus h squared is equal to c squared t1 squared. By the way, where does it stop? Since you're saying it's kind of cutting off.
All but the last line, the very last line, we can't see, but the second to last line is visible.
So when I go to it, I'm gonna, okay. So you can still see this one, right?
Yes, that's right.
Okay. So the next thing we do is we subtract v squared t1 squared from both sides to obtain that h squared is equal to c squared t1 squared minus v squared times t1 squared. Then we can actually factor out our t1 squared to obtain that h squared is equal to t1 squared times c squared minus v squared. Then what we do is we divide both sides by c squared minus v squared to obtain that h squared divided by Sweden squared minus v squared is equal to t1 squared. C, not Sweden.
I was very confused when you said Sweden.
I accidentally said Sweden. Okay, so then we square root both sides, and what we obtain is that h divided by the square root of c squared minus v squared, right? Because we can distribute the square root, the denominator and the denominator. That is just d1. T1, my goodness. Fucking Sweden. Anyway, so this is our relative time, right? Now, what we do is we divide the numerator and the denominator by c, right? So, in other words, we multiply it by 1 over c. So, what do we obtain is that h over c, right, divided by 1 over c times the square root of c squared minus v squared is equal to t1. Now, take a look at this final equation that we have over here. So, is it visible?
Yes.
Yep.
Okay. So, T1 is actually equal to, this expression, except what I did is I put the 1 over c in the square root by squaring this expression, because we recall that the square root of a product is the product of square roots, right? So then what I did is I distributed over this 1 over c squared, and what would happen is you get c squared in this numerator. C squared over c squared is 1, and then you have 1 over c squared times v squared. So, well, the v squared would go in the numerator, and what you end up with is that t1 is equal to t naught divided by the square root of 1 minus v squared over c squared. Which is a pretty interesting expression, because what we get is an expression for the relative time in terms of our stationary time. And in fact, we notice that the only arbitrary pretty much choices we made were the height that where the light bounces, and the speed at which it is moving, and both are taken into account. Remember, we didn't specify a height; we just denoted it with age, so that's good. And as you can see, it does take the speed into account. Thus, we have obtained a general formula, a general equational description of time's relativity. So let t naught and t1 represent stationary and relative time respectively. Furthermore, consider gamma to be equal 1 divided by the square root of 1 minus v squared divided by c squared. Then t1 is equal to gamma t naught. In fact, this gamma, it has a special name. It's called the Lorenz Factor. And it's a factor of how much time becomes scaled. And it's pretty much like a function of speed, if you think about it. Now, let's look at a couple consequences of this. Let's kind of play around with this, right? So, what happens if our speed is 0, right? So, you would plug in 0, so what you get is 0 squared divided by c squared, well, that's 0. So, you get 1 minus 0, that's 1. Square root of 1 is 1. What you get is 1 divided by 1. So, it's 1. And you get that t1 would be equal to t naught, which is correct because we had no speed. We were stationary, so it should check out. Now, you will notice that the more we approach the speed of light, okay, let's see what happens as this, actually, first, let's see what happens when this value is relatively small. And when the value is relatively small, this is approximately 0, so this is approximately 1, so you get approximately the square root of 1, which is approximately 1. 1 divided by approximately 1 is approximately 1, so realistically, when you have small values of speed, they will not affect the time perception. And notice that as we go to the speed of light, gamma actually becomes infinite. Right? Even if we plug in c over here for v, what you get is c squared divided by c squared, that's 1. What you get is 1 minus 1, that would be 0. Square root of 0 is 0, you get 1 divided by 0. Right? So, what gamma actually does, as v tends to c, is gamma actually tends to infinity. So that is pretty crazy. Now, one example might include, imagine having two very exact clocks, okay? And you place one stationary on the ground, okay? And you get one in an airplane. And what you do is the airplane, for example, goes for a day at a very high speed, and then you place it on the ground, and you'll notice that the clocks will now go at the same speed on the ground, but what happens is one is a bit late, the one that was in the airplane, because the time for that was a bit faster. But we have to take into account what actually is the first postulate of special relativity, which tells us that the laws of physics remain the same in all initial frames of reference, right? So, to demonstrate this, so I'm actually going to take a famous example called the twin paradox. So, the twins, right? When you have two twins, they should, by the definition of a twin, remain the same age. Now, let's say that you have one twin who gets into a rocket and then is shot into space at a very high speed, is there for some time, and then goes back at a very high speed. So what is he gonna notice is that despite him being kind of young, like there wasn't much time if it happened, his twin would now be older, because the time passage there was slower. Now,
Sorry, to be clear, can you say that again? So the supposed paradox you're saying is that the twin who stays home, let's say twin A stays home on Earth, twin B gets on the rocket ship that you described and goes away very fast for a while, and then comes back. So the claim is that it's a paradox. Why? Because when he comes back, twin A appears older than twin B. Is that the claim?
yeah, basically.
Good. Okay. So I will ask a question, which is, I think, a reason why many students learning the subject become confused. So they might say, okay, by relativity, any inertial frame is equally good. So I can think about either twin A's frame or twin B's frame, right? So from twin A's perspective, he's staying stationary the whole time. Twin B goes away and is moving at some very high speed. So by time dilation, time passes more slowly for twin B. And then when he comes back, since time passed more slowly for twin B is younger than twin A. Okay, fine. But from twin B's perspective, as you just told us, like for me on the bus, from twin B's perspective, it looks like he's stationary, but twin A is moving. So from twin B's perspective, he's sitting stationary the whole time. Twin A is moving very fast, because even though he's back on Earth, from my perspective, it looks like he's moving. So I apply the formula you have here. Twin A has some gamma factor that means time is moving more slowly for him, so he should be younger. And then when I come back, you would say, twin B applying this formula should argue, oh, time moved more slowly for twin A, so he should be younger than me. But that's a contradiction, right? It seems like each twin argues that the other one should be younger. So who's right? What is the resolution to this paradox?
That was the first postulate talks about.
No, I don't think this has anything to do with the first postulate, right? I mean, what's the resolution of the contradiction? I mean, which of the two is? Well, okay, I guess maybe I should let you explain what you mean by how the first postulate resolves it. But well, okay, I'll leave that contradiction.
You can go ahead. You can go ahead.
If by the first postulate you mean specifically the resolution is that the word inertial is there, then I would agree that's a resolution to the paradox, because twin B was not in an inertial reference frame. He had to accelerate to get very fast. If that's what you meant by the first postulate resolves this, then I agree. But
yeah, that's the point.
Okay, good. Well, then I'm happy. That is indeed the resolution.
Okay. All right. So, I guess I'm done with this slide for now. Now, we're going to be talking about some consequences. So, for example, there's a phenomenon called length contraction. So, we recall that length is defined, well, not really defined, but it is equal to the speed times the time that it takes to beat that distance with the speed. So we can set S naught as VT naught. And now if we think about S1, that would be equal to VT1, but we recall that T1 is equal to gamma T naught. So this is actually equal to gamma VT naught. Hence, length is scaled by the Lorenz factor. So we realize that S1 would be equal to gamma S naught. Another consequence is we notice that M is equal to FA and F divided by A, and we recall that A is nothing but the ratio of speed to time. So what do we get is F over V over T. And what we can do is we can flip this fraction, right? We can basically multiply by its inverse instead of dividing by it. So what we will get is F times T divided by V, or in other words, Ft divided by V. So M naught would be equal to Ft naught divided by V. So M1 would be equal to Ft1 divided by V, which is equal 2, and recall that t1 is equal to gamma t naught. So what we obtain is gamma times ft naught divided by v, and we realize that ft naught divided by v is our m naught, hence mass is scaled by the Lorenz factor m1 is equal to gamma m naught. Now, let's think about the work integral. So, we recall that work is equal to force times displacement. Now, what if the force changes, right? For example. Now, we recall the concepts of an integral and how it solves the problem. You can sum all the little forces, okay, that happen there across across an interval. And by summing them, the product with this little length, what you would get ultimately after this sum is the work. So the work can actually be defined as an integral from 0 to x of f dx. But now, f is equal to ma by Newton's second law, but also if your acceleration changes, it can be defined as f is equal to the derivative with respect to time of mv. Now, we apply this and we make f equal to the derivative with respect to relative time of relative mass times speed. And we recall that m1 is actually m naught times gamma, where I literally wrote down the value of gamma that we derived earlier. So this derivative expression is actually rewritten as m naught v divided by the square root of 1 minus v squared divided by c squared. After applying the chain rule, the quotient rule, and a bit of kinematic intuition, this is the result, which I'm not going to completely derive, so you'll have to trust me on that one. So, the work, right, so what we can do is we can take our original work integral and we can plug in our new value for capital F. So, you would get m naught, right, instead of this f, you would get m naught a divided by 1 minus v squared divided by c squared to the power of 3 over 2. But m naught is actually a constant that you can pull out of the integral, because the stationary mass will not change in this integral. So, what you're left with is this, but we realize that a, or the acceleration is nothing but for a small change in time, what is the resulting change in the speed, right? So, in other words, the derivative of your speed with respect to time. And now, I'm gonna pull a little Luigi. If somebody doesn't know the meme, I can send it in chat for a second.
You should probably send the meme so people don't think that you're literally schizophrenic for saying Luigi.
Okay, so I've sent it the maths talk discussion.
Oh, very good.
Okay.
I'm pulling up the meme for people watching the recording so they can see it. And
okay. Yeah, so I'm going to pull a little Luigi here, and I'm going to treat this as a fraction. So, as I said, this is not completely rigorous. But what I do is I multiply the numerator and the denominator by dx, and by commutativity of multiplication I can interchange these, and this, actually, I split it by properties of fractions into this derivative of speed with respect to x and dx with respect, right, to t1. And we realize, actually, that the derivative of distance with respect to time, right, for a small change in time, what is the resulting change in distance? Well, that is just quite literally the speed, so we rewrite it using v. So we plug it in over here, so we change this a for v times dv over dx, where this dv over dx is put out of this fraction, it's right next to it. Now I pull a Luigi again, and I cancel out these dx's and rewrite the boundaries in terms of v, to obtain that this actually is equal to m naught times the integral from 0 to v of v divided by 1 minus v squared divided by c squared to the power of 3 over 2 dv. Is this entire slide visible?
All except the last line with the delta E, looks like.
Okay, so I'm gonna show it later on, but so we let u be equal to 1 minus v squared over c squared with these unnecessary brackets, and this implies that du would be equal to negative 2v divided by c squared dv, because the derivative, du over dv, well, 1 is a constant, we ignore it, we have negative v squared divided by c squared. Well, the speed of light is also a constant by the second postulate of special relativity. So we can pull it out of our derivative. What we get is negative 1 over c squared, right, times the derivative of v squared. That would just be 2v. So what you get is that derivative, that derivative du over dv is nothing but actually negative 1 over c squared times 2v. And you can place the 2v, you can multiply with the 1, right? So get it in the numerator. And then you can multiply both sides by dv. And what you obtain is that du is equal to negative 2v divided by c squared dv. And now we go back to our original integral, except without the boundaries. We now are working with our indefinite integral, which we'll later, right, evaluate from 0 to v. So what we can do is we can, inside of the integral, we can place negative 2c squared times negative c squared over 2. Because the negative signs would cancel out, and the c squared with the c squared, they would cancel out, and the 2 would cancel out with the 2, so that would just be multiplying by 1. So we multiply by that, but then we actually do a sneaky little and we pull out the negative c squared over 2 out of our indefinite integral. Just leaving the negative 2 over c squared, right? V is multiplied, right? That would give us 1. And then we put the v on in this numerator over here. Now, we actually remember that this is our u expression. This is our du. This is exactly our du. So we replace it with the du, we're just left with a 1 here. And we replace this expression with our u. And now we can actually rewrite this in terms of a negative exponent. So this, the entire expression is actually just negative c squared divided by 2 times the integral of u to the negative 3 over 2 du. Yeah, I went backwards accidentally. Now, what we can do is we can apply the power rule and conclude that this is actually equal to negative c squared divided by 2 times u to the negative 1/2 divided by a negative 1/2. Now, the negatives cancel out. Now, instead of dividing by this fraction, you could multiply this by the inverse of this fraction, so that it would just be 2, right, since we've canceled out the minus signs. And the 2 would actually cancel out with this 2 in the fraction with the c squared over 2. So we're just left with c squared over here, and then times u to the negative 1/2. So this is just 1 over u to 1/2, and u to 1/2 is just the square root of u. So what we actually obtain is c squared times 1 over the square root of u. Now what I do is I place the c squared in the denominator, and I replace this u with what it originally was, which is 1 minus v squared over c squared, and obtain my indefinite integral. We've integrated this bad boy. Now, what we can do is we can substitute from 0 to v. Now, if we substitute v, shit happens. It's already an expression in terms of v. And if we substitute in 0, well, you'll get 0 over c squared, which is 0. 1 minus 0 is 1. C squared divided by the square root of 1 is obviously c squared. So this is our expression. Now, we remember that work is equal to m naught times the result of this integral. This is the result of this integral. So work is actually equal to m naught times this expression, which if we actually distribute the m naught, over here we realize that we're just left with m1 times c squared, and to the other one we just get m naught c squared, right? The reason we get m1 is we have m naught divided by the square root of 1 minus v squared divided by c squared, which is by definition m1. And we can actually factor out c squared, and what we get is that this is equal to c squared times m1 minus m naught. Now we recall that the change in kinetic energy is equal to work, which, as we said, is c squared divided by m1 minus m naught, which is equal to c squared times the change in m. Now we realize that c squared is constant, so if you want to obtain a formula for this in a stationary frame, what you can do is you can remove the concept of change from both sides and end up with the mass energy equivalence, the Einstein's formula. The fruit of special relativity is Albert Einstein's famous formula relating mass and energy, which is E equals mc squared.
Sorry, I actually got confused at the last step. So how did we conclude this was a change in m and not just a change in kinetic energy or the velocity or something? I think there was some step at the end I missed. This delta E, which we read off, this work is delta M on the last slide.
Yeah, it was delta E is equal to delta mc squared, right?
Yeah, how do we conclude that? I mean, if I do work, you're assuming it's stationary, so you're assuming, why can't I do work on an object and not increase its rest mass, but increase its velocity the way that I normally would? How did we determine this wasn't going into a change in the velocity?
Could you repeat your question?
Yeah, could you go back one slide to this 12, this stuff? So, we computed the work.
This looks like cum.
It does. That's mysterious. Work is m naught times. This is confusing. So you argued that the change in energy is the work, which is the maybe this is a question about the interpretation of this or something like that, but I mean, ordinarily I would say I do work on an object, and that increases its kinetic energy, for instance, by increasing its velocity, for instance. But here you're saying the change in kinetic energy is... Oh, I see the confusion. Okay, sorry. It's because we're using this somewhat outdated notion of this relativistic mass instead of rest mass. Okay.
Yeah.
I mean, the way I usually think about it in the more modern perspective is the mass never changes. The mass is always the same, but the momentum has a factor of gamma in it. But these older textbooks or high school textbooks indeed sometimes talk about this change in relativistic mass where the mass changes. So my confusion was, why is it that the energy is changing the mass? But what's really happening is the work is indeed changing the kinetic energy of the object measured by gamma mc squared, but you're interpreting the product gamma m as a relativistic mass, so it's changing the quote-unquote relativistic mass. Okay, good.
Yeah.
Then I'm happy.
Yeah, there was a concept of relativistic mass I introduced in a previous slide.
Yeah, I don't like that concept, but yeah, that's fine.
Yeah, I don't necessarily either, but...
Yeah.
I had a couple of questions. So, slide 11, you're working out work as an integral, like a function of v. You set the upper limit in the integral to v, like the integration variable. Is that like the same v? Because you end up plugging it into your like antiderivative function, right?
Yeah, this is the same v.
No, okay. One should be a v prime. I think what K-Star is getting at is in the last line, the integral from 0 up to v. That v is a different quantity than the v appearing in the integrand. The thing in the integrand should be a v prime or something because it's a dummy variable. So we're abusing notation somewhat by using the same v twice.
Okay, true.
Yeah.
Also, slide 10 about like length contraction. So the Lorenz factor is greater than 1, right? And doesn't that mean that S1 is going to be bigger than S0? Because you're timesing S0 by gamma. So why is it called a contraction? Wouldn't it be like extending? I don't know. Or is that just what it's called? I don't know. Maybe that's just me misunderstanding.
You have to remember which frame is which, right? Because the length factor, which is greater than 1, multiplies S0 to give you a length that's measured in S1. But S0 is the length as measured in his notation by the moving frame. So if you wanted to solve for S0, the length measured in the moving frame, in terms of the length measured in the rest frame, you would divide by gamma, and you would say, the moving guy measures a length which is reduced, it's divided by gamma compared to the length in the rest frame. Because it's always, an object is always longest in its rest frame, right?
Right, okay. You could divide it by gamma, right? Both sides.
Okay.
So you'll get S1 divided by gamma is equal to S0 as well. That's quality.
I have one more final question. So you said by the second postulate, the speed of light was constant. I thought that was the first postulate when it says like it's about 300, million years per second or whatever?
300,000 kilometers per second.
Right.
Approximately.
Yeah. Okay. Wasn't that the first postulate? Yeah.
That is actually called second postulate. In the presentation, I called it the main postulate.
Okay.
Just because I believe it's to subjectively,
Okay.
To
So then what is
probably the most important concept, which leads you to all of the later conclusions, right?
Mm-hmm. So then, what is the first postulate? If that's the second postulate, what is the first postulate?
I believe I did mention it. So, basically, the first postulate states that the laws of physics remain the same in all inertial frames.
Okay, cool. All right.
So that basically states that, while relativity does make the world a bit fucked up, it's not super, super, super fucked up.
Yeah, sorry, I must have missed that then. Never mind. Cool.
Alright, so I hope it was a bit humorous. I hope it was a bit, that you've learned something. And, yeah, that was it, I suppose. Can I stop screen sharing now?
Yeah.
I guess, honestly, there's presumably questions or discussions, so maybe we should open it up if anyone has questions that refer to the slides so that it would be useful to keep the screen share for that part. But,
Alright, okay. I can keep it.
Good. Questions from anyone then?
I have to read the chat.
Yeah.
What did I miss? Is that Poland? That explains the feminine body. I think I'll leave the server. It was quite a weird one. Ferko chuckle. Sweden squared.
When you said the guagre or whatever, his reaction was quite priceless. He just almost spat out his coffee or whatever. It was great. I didn't quite get a screenshot of it, but I'll get into it.
Actually. Axiom of Infinity has a question saying, I kind of missed the twin paradox, so what's the actual solution? Twin A being older than twin B, or the other way around, or both having the same age?
Yeah, I also missed that.
Go explain it, Chris. I'm not good at explaining the twin paradox.
Oh, good. So yeah, the resolution which he was alluding to is that in this story, if twin A stays on Earth and twin B goes onto the rocket ship and flies away and comes back, when twin B returns, it is indeed true that twin A will be older than twin B. The person who left on the rocket ship and came back is genuinely experiencing a measurable let me say it in a better way. From the perspective of the person on the rocket ship, there's a genuine time dilation, so that the twin A who remained on Earth is genuinely older when twin B returns. That's the statement. It's slightly confusing, I think, because of the acceleration issue that I brought up in that question. That's that twin B has to accelerate in order to go very fast. Because when I've taught this before, I think students will often have questions that are similar to the twin paradox, but in a simpler setting that does not involve any acceleration. So anyway, the answer to the previous question was indeed, the resolution of the twin paradox is there's no paradox. Twin A is older than twin B upon return. That's fine. Now let me ask an even simpler paradox. So Aptrock showed us this formula for time dilation that involved a gamma, T1 equals gamma T2, right? So
T1 equals gamma T naught. This.
Or sorry, T naught, yeah. However,
it's notational. It doesn't matter.
Yeah. So here's an error that causes students to make incorrect conclusions in exams all the time. So suppose, as in the bus example, I'm moving with respect to Aptrock, and I'm moving fast enough so that gamma is, say, 1/2, which is 2, to make the numbers easier. So if I look at my watch...
Wait, again? What was your gamma value?
Just pick an easy number, like gamma equals 2 or something, right?
Dude, at what fucking speed is that bus going? Dude, you're gonna be taking away your license, and your career of being a bus driver will just go down. Like, it will go down instantly. In fact... No, dude, you're gonna have like so many years of prison.
I will certainly lose my license if, assuming I survive this trip, moving at an appreciable fraction of the speed of light. But
I mean, I'm gonna solve an equation. I'm gonna check exactly how much speed you would need to have.
Yeah, but what were you saying?
So the confusion is. The confusion students often have is in applying this formula symmetrically in the following way. So the student might say, okay, I'm on the bus, I'm moving, and I'm moving with the speeds with respect to Aptrock such that gamma is, say, 2. So then the student might reason, okay, suppose I look at Aptrock's watch, and during a period of time I see his watch tick by 1 second. So I'm measuring a time lapse of 1 second in his frame or something. So then I argue, oh, well, by this gamma factor of time dilation that he wrote down, where T1 is gamma T naught or whatever, if I see the clock tick on Aptrock's watch and it's ticked by 1 second, I have this gamma factor of 2, so I should conclude that times dilate. So the true time that he measured should be larger than this. I should say that the time in his frame is 2 seconds, because I dilate gamma by 2. On the other hand, Aptrock then in his frame, suppose that argument were correct, and he in his frame looks at the watch and sees it tick twice in that period of time, so that 2 seconds have elapsed. And then Aptrock would argue, oh, well, Chris is in the bus, he's moving with respect to me at a speed that makes gamma equal to 2, so times dilate, so his measurement of the amount of time that passes on my watch, which I've measured to be 2 seconds, will be dilated by a factor of 2. So he will see a time lapse of 4 seconds. But this seems like a contradiction, right? Because the one argument said, oh, it's 1 second, so it's actually measured to be 2 seconds, and the other argument is it's 2 seconds, so it actually should have been 4 seconds. So it seems like something's wrong, that we can't always apply this time dilation formula and say, oh, in any pair of frames in relative motion, times will dilate, because it leads to a contradiction. This is how people make errors in exams. They think, oh, time always dilates, so I always multiply by the gamma factor when going between relative frames. And you can see how this is incompatible. The resolution, of course, is to remember that times are always shortest as measured in the object's rest frame. It only dilates if you're comparing time measured in a moving frame to time measured in the rest frame. So you don't just always dilate, right? You have to remember, if it's in the rest frame, it's the shortest amount of time. If it's measured in any moving frame, and then it's always a longer amount of time compared to the rest frame. And this is good to keep in mind. This is like the simpler version of the twin paradox, right? Where it's like me and the bus, who's right about the time being longer in one frame compared to another? And the answer is, okay, in the rest frame, it's always shortest, in other frames, it's always dilated. Anyway, that's
let's call it that Chris goes at 259,807 kilometers per second paradox.
Yes, I like doing that. That's my hobby on weekends is to move that fast.
Gotta go fast. Is in a particle accelerator on weekends.
Yeah,
You're gonna lose your bus lesson.
That is my hobby.
So, yeah, listen, I have a recursive hobby. My hobby is telling people that I have this hobby.
And it persists ad infinitum. Good.
Right.
Other questions? Hopefully we're happy with the twin paradox after that longer discussion.
I have a recursive. Listen, Spectre's quotes are always like they're quotes. What else can you say?
I am Reverse Thompson from Reverse Flash. Okay, there's no questions. I'll introduce. So another cognitive dissonance people sometimes have when they hear this statement. So the speed of light is a constant as measured in all inertial frames. Okay, great. So you're told the speed of light is a constant. It never changes. It's always c, blah, 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 blah. Then when you study optics or maybe in an introductory physics class, you're told there's something called the Index of Refraction. The Index of Refraction measures the speed of light in a medium compared to the speed of light in vacuum. So you're taught in this class the speed of light is slower in water or in glass or in any other transparent medium than it is in vacuum. But now again, it seems like there's a contradiction, right? How is it that you're telling me the speed of light is a constant and it's always the same for all observers and it's always c, but on the other hand, light slows down when it goes through glass or water? It's another thing people get confused by, I think. So I'll pause if anyone wants to resolve that or express opinions on that supposed contradiction.
I don't know if this is right, but is it just like the photons enter your medium or whatever, let's say it's diamond or something, and it's like hitting the electrons in the, like, it enters at the speed of light in a vacuum, right? But then it's hitting like the electrons in the carbon atoms or whatever, and they're like emitting their own photons, so it makes it seem like it takes a long time to get through the diamond structure or whatever. So like it's not actually the speed of light that's slowing down, but it's just taking a while to emit and go through like the whole crystalline structure, I guess.
That's right.
Yeah, as the name suggests, it just refracts in the medium.
Yeah. Well, it's not refraction. So this has nothing to do with refraction, but it has to do with absorption and emission, as K-Star was saying. So independent of whether it refracts, it'll slow down because of absorption and emission, which indeed, I mean, the answer to this confusion is, what you learn in optics is only an effective theory that describes, some approximate emergent behavior so that the light appears to slow down. But fundamentally what's happening is exactly as K-Star said. The photon is always moving at the speed of light. It just so happens that it gets sidetracked, occasionally being absorbed by an electron and re-emitted and bouncing around and spending some time doing that, which appears to slow down its effective speed as it travels through the medium. So, of course, there's no...
Starts goofing around.
Yeah, you could say it likes controlling with electrons or something.
A little tomfoolery.
Yeah. Playing some games. This is very nice. This is a nice talk. Very deep ideas that motivate a lot of other stuff. You could also play the same game with this talk as we did in the gauge theory talk, right? So you could say, in the gauge theory talk, there's a symmetry where you rotate the phase of an electron, and I can do that globally. And then you ask, what happens if I rotate the phase of an electron locally, and that gives you electromagnetism? In this talk, you could say, Aptrock is telling us there's a symmetry where I can change inertial frames, so I can boost, essentially. I can globally change my inertial frame, and that's a symmetry of the physics. That's what he was calling, I guess, the first postulate, essentially, that there's a symmetry when you change inertial frames. Then you can ask the same question, can I gauge that symmetry? What happens if I say, not only can I globally boost and change inertial frames, but can I locally boost and change inertial frames by a different amount at each point? What gauge theory does that give you? And that is one way of viewing general relativity. You can view general relativity as the gauge theory for local Lorenz transformations. This is how you describe relativity in, say, the tetrad formalism. It's some gauge theory for local Lorenz transformations, which is very cute. I like that. Yes. Shilling the gauge theory talk. That is correct.
Right, so I believe that's it. Question mark in parentheses.
Much shorter discussion than yesterday's talk. Other thoughts from anyone else?
I am satisfied. I don't have any questions. But...
Okay.
Yeah, I expected more people to come because like 10 people signed up, I believe. So I feel immensely disappointed. That aside, thank you guys for attending. It was kind of stressful, but at the same time, when I realized, like, dude, this is the Gregorius maths community, you know, I kind of became relaxed. So thank you very much, guys, and yeah.
Very good.